So when it comes to finding an inverse, right, the first thing we're going to do, it's kind of like a preliminary step almost, you might say, we're going to change f of x or g of x or h of x, whatever you might have, to y. So change the function, change it from function notation to just like the variable y there. Okay. So now we should have everything in terms of y's and x's. And then what should we do at this point? Now what's our kind of our next step? Once we change that f of x to y, what do we do with our variables? Switch them, right? Swap them, right? So we'll swap the x and y. Very good. And now the x and y's are swapped. The next step we should do is what? Solve for y again, because now y is kind of mixed in with the the function or the equation there. And so now we'll solve for y, get that y by itself again. Okay, and then that's kind of it, although really we should then rename the y again as f inverse of x, okay? And it's that little f to the negative 1 of x, which is kind of a confusing notation in my opinion, because every other time we see something raised to the negative 1 power, what does that mean to do? Yeah, like the reciprocal, 1 over whatever that quantity is, and which is not the case here. This means inverse, okay? If you want to do like the reciprocal of a function, you'd want to write something like this. Okay, so this just means inverse. Okay, so just be careful with that. If you want to get the reciprocal of a function, you kind of put like a parentheses or brackets around it. Okay, it's just kind of a strange notation. And the idea of a reciprocal and an inverse are different ideas, right? They're different ideas, okay, except for multiplication, where that is kind of the same idea. All right, but for other, for functions and stuff, an inverse is not necessarily just a reciprocal. Okay, let's try an example here then. So let's find the inverse of the function. The functions. Okay, so number one, we'll do one here together. H of x equals 2x plus 6. That'll be our first function there. Okay, so we'll change the h of x to y. Just like that, right? And then now how should we proceed from here? What should be our next step? Swap the x and y's, right? You got it. And now we what? Solve for y. Okay, so to solve for y here, what should be our first step? Subtract 6 on both sides. You get x minus 6 equals 2y. And then to finish solving for y here, what do we have to do to both sides? Divide by 2. Okay, so when we divide in an equation, when we multiply in an equation, remember that you're dividing the entire side, or you're multiplying the entire side by whatever number, okay? So when I divide both sides by 2 here, I'll divide this by 2, right? There's just one term, so only that one term gets divided by 2, and the 2's cancel, so we'll have y equals. But over here we have 2 terms, and so it's going to be x minus 6 all over 2. Okay? Now when we started, we had h of x equals 2x plus 6, okay? What would the graph of this look like? What would it be? What kind of graph is it? What kind of function is it? A what? Line, a linear function. That's right. What about this though? What is its graph? It's also a line. It's also a line, but it's in a bit of a weird format. Right here, this is like a very clear slope-intercept form. 2 is your slope, 2 over 1, and then 6 is your y-intercept. Here, it's a little bit less clear because we have this like whole thing being divided by 2. But remember, you can simplify a little bit further here and say, oh, that's really 1/2 x minus 3. So in other words, you divide the x by 2 and the minus 6 by 2, right? You can break up a numerator over your denominator there. So 1/2 x minus 3, and then that's easier to graph. And really, I should not stop there. I should go back and say, okay, that's really h inverse, okay, is equal to 1/2 x minus 3. So should you be asked to graph a function and its inverse, so like this function and the inverse here, okay, you want to make sure that you can manipulate that inverse around to get into a format where you're comfortable graphing it, okay? You want to make sure you can manipulate it around so you get into a format where you're comfortable graphing it. All right, questions on any of that? All right, if not, I've got one for you to try here. All right, so f of x equals the square root of 2x minus 3. Okay, so you try that one. F of x equals the square root of 2x minus 3. Come up with the inverse there. Or you can put 1/2 instead of x squared over 2. You want to put 1/2 x squared. That's what you're fine with what you got to do too. How about Sam? Samantha, you want to give us, how did you do this?
Okay, so I changed f of x into y equals square root of 2x minus 3.
Okie dokie.
And then I switched the x around.
Okay.
X equals square root of 2y minus 3.
Just like that, okay.
And then I squared it.
Square both sides, all right.
Yeah. So then it was x squared equals 2y minus 3.
So far, so good.
And then I added 3 to both sides.
Okay.
X squared plus 3 equals 2y.
Okay.
And then I divided both sides by 2.
Uh-huh.
And I got x squared plus 3 over 2, or x squared over 2 plus 3 halves. And
Okay.
then I
Whoop.
changed it into f, was that negative 1 of x?
Yeah, f inverse. F inverse is fine. You can say that f inverse of x, okay, equals, and then you just wrote the x squared over 2 plus 3 halves. Okay. So there it is. Questions on any of that? No questions? Okay, we're good? All right. All right. So then let's take a look at how we're going to verify inverses. So we're finding inverses here. We're also talking about verifying inverses. So okay, how do we like kind of check to see if things are in fact inverses of each other? Okay. Does anyone remember how you can check to see if two things are inverses of each other? What can we do? Okay, so kind of set them equal to each other. We plug, yeah, there you go. That's exactly right. Yeah, we're going to plug one into the other. That's right. So actually, I think I put it better here. Let me get this one out. So, and I'll call that like the algebraic method, I guess I'll say. Algebraically. Okay, and then yeah, if f and g are inverses. Okay, so if f and g are inverses, which means then you could really say g is f inverse, right? But we don't know they are just yet. So we have these two functions we're thinking maybe they're inverses. If f and g are inverses, then f of g of x should equal what? Not 0. 0 is the additive identity. We want x. For functions, it should equal x. The function identity. Okay? Is that sufficient, though, to show that these two functions are inverses of each other? Is that sufficient? Well, Mr. Whitmire, you're asking the question, so I kind of like, and what else must be true? G of f of x must also equal x. Okay? So you must check both directions, okay, for proper kind of like justification of an inverse. All right? If it's not sufficient for you to show it one way and say, I'm done, that's not proper, okay? There are situations where you plug one function, you plug g into f, you'll get x, but you plug f into g, you might not get x, okay? So you want to make sure that you're checking both directions there. All right? That's one way to check if we have inverses or not. What's another method? Anyone remember? Colby? Yeah, we could graph them too. And how does it show? How do the functions kind of show up, or what about them? How are they related graphically?
I thought they were about the x and y axes.
Say again.
So are the inverses flipped over both x and y axes?
They're reflected over something. It's the line y equals x. The line y equals x. So a function's inverse. Okay, the inverse of a function, or a function's inverse, is the reflection of the original function over y equals x. Okay, I actually want to talk about this one here for a second too. Okay, so again, we have two ways that we can verify inverses. One, you plug the inverse into the function, you should get x, and then you should also plug the function into the inverse and get x that way. And then the second method of making sure we have an inverse is to look graphically, right? That is, a function's inverse is the reflection of the original function over y equals x. We can actually see that here with what we did. So I'll show you here real quick on my graphing calculator with the h, and then we'll also look at f here as well, at f inverse. All right, so clear out stuff here. All right, so let's graph this. So 2x plus 6, and I'll graph the 0.5x minus 3. And then because I want to show that it's reflecting over the line y equals x, I'm going to graph the line y equals x as well, just so you can see that reflection. All right, so there's our original function, h. There's h inverse, and there's y equals x. Okay, and you can see that reflection there too. If I change it to zoom square, just so you kind of square up the graph there, it makes it maybe even easier to see. I don't know, but there it is too. Okay, so you can see that reflection, right? Very easily. Okay. So let's look at this one then. I'll keep the x in to show that line of reflection. I'll put in the square root, 2x minus 3. And then I'll put in x squared over 2 plus the 3 halves that Samantha gave us there. All right, so there's our function and its inverse. So there's the original function. There's its inverse. And there's the line y equals x. Uh-oh. Does the function and its inverse exactly match up? Are they exact reflections of each other over the line y equals x? No, they are not. So, are we correct with the inverse that we wrote here? Well, we did the right stuff, didn't we? I mean, we swapped the y's and x's. We solved for y. We got this. Okay, so the method was right, but they don't quite match up. Okay, so we have to throw in a little bit of a correction here. Okay, if this is our original function, this is going to reflect to this part of our inverse right here. And so we want to limit our inverse so that we're only going to include this part of the inverse. Okay, so how can we describe that? Well, it's for x values greater than or equal to 0. So we need to throw in a constraint here. Okay, we need to throw in a constraint. X x greater than or equal to 0. Believe it or not, you can actually constrain your graph in your graphing calculator. So if I go to my inverse here, and I'll put parentheses around it, I'm going to divide by my constraint, parenthesis x, and then to get the greater than or equal to symbol, if you press second math button, it gets you the test menu, and then there's the greater than or equal to symbol right there, and I'll do 0. Okay. Now, what this little command does here, why I divide by this, is it uses kind of like Boolean logic, for those of you that maybe have like taken some programming stuff like that, okay? This, because when your calculator goes to graph stuff, it's plugging in a bunch of x values, okay? So it's going to plug the x's into the inverse, but it's also going to plug the x values in here. If the x values it plugs in, the calculator plugs in, are greater than or equal to 0, this command will return, the output will be a 1. So we'll take our function at that x value, divide by 1, if the x value is greater than or equal to 0. Which is like a true, right? 1 means true in like Go and stuff like that. If the x value is not greater than or equal to 0, this will return a 0. We'll be then effectively dividing by 0. This will not graph because you can't, the calculator won't be able to graph something when you divide by 0. And so as a result, there's our function. There's its inverse with the constraint. And there you can see that line y equals x. And we now have, the exact, inverse there. Okay, that constraint. This idea that I did right here, dividing by x greater than or equal to 0, you can use that when you want to graph a piecewise function. Say that your piecewise function has 3 pieces in it. You would put one piece per y equals here. So y1, y2, y3 is what you'd have it in. And then you divide, put parentheses on the pieces, and divide them by whatever their constraints are. And that's how you can graph a piecewise function in your graphing calculator too. Okay, so that's another object there. Questions on any of this though? Does that make some sense at least, hopefully? Okay, so you want to make sure that your function and its inverse actually match up and stuff. All right. Got a little bit more here. Just a tad bit more. Okay. Oh yeah, I got one for you to try. Here we go. So I want you guys to try this one. Verify that f of x equals x squared, nope, not x squared, x cubed minus 1, and g of x equal to the cube root of x plus 1 are inverses. Okay. So verify that f of x equals x cubed minus 1 and g of x equals the cube root of x plus 1. Verify that they are, in fact, inverses of each other. I'll do that too. Time's up. I did this. Okay. I plugged one into the G into F and F into G, right? So they both equal X. And they do. Okay. You can graph it, but really, like, the graphing is kind of like hard. I don't know. The justification is not as precise. This is a much more precise justification, I would say. The graph, you're kind of like, they look like the reflections of each other, right? But this one, you can definitely see, aha. G plugged into F gives you X. F plugged into G also gives you X. Therefore, they have to be inverses of each other. Okay. That's really the most solid justification. If you're just trying to, like, you know, quick and dirty figure out if they are, then yeah, you can just definitely graph it. All right. One more idea here I want to throw at you. Okay. And it's this concept in math called one-to-one. Okay. So, something is called, a function is called one-to-one, or a function is described as being one-to-one. Okay, if its inverse is also a function. Whoops. Okay. Function is one-to-one if its inverse is also a function. There we go. So, and the idea, like the meaning behind the phrase one-to-one, right? It's not super creative, but it is an intentional, you know, word for what we're describing here. So, when it comes to a function, right? We are like something is if something is a function, that means each x goes to only one y value, right? Every x goes to only one y value. So, for example, 3 can go to 2, but 3 cannot also go to 5, right? This would not be a function because you have the same x value going to two different y values. Or you might say 1 to 2, right? One x value going to two different y values here. And that doesn't work, right? A function cannot be 1 to 2, okay? But a function can be two to 1, okay? Or 3 to 1, or 4 to 1, or 5 to 1, right? You can have any number of your different x values going to a single y value, right? In fact, a horizontal line, it's like infinity to 1. Every x value for a horizontal line goes to a single y value. So you can say it's infinity to 1, okay? This is okay for a function, okay? So it's okay for a function to be, 2 to 1, okay? We can't go 1 to 2 like that. But then for 1 to 1, this would not be okay because 2 is going both to 3 and the 5 is going to 3 as well. So for 1 to 1, this would also not be okay. So what 1 to 1 literally means is every one x value goes to only one y value, okay, and reverse. Every one y value is paired with only one x value, okay? There's no doubling up in either case, 1 to 1. Okay? Now, the test we have for determining if something is a function, what do we call that? Graphically, we call that the what test? Vertical line test, right? Well, if we determine if something is a function by a vertical line test, and a function's inverse is a reflection over the line y equals x, right? We won't have the vertical line test anymore. We'll now have the what? Horizontal line test. And that's exactly what we're going to use here. So the horizontal line test okay, if any horizontal line, again, this is not very elegant, but you get the idea. If any horizontal line passes through, or intersects, if you like, two or more points of a function f, then f prime is not, sorry, not f prime, then f inverse is not a function. Whoops. Okay. So again, f can be a function, but if you draw a horizontal line to any part of f, and that horizontal line hits more than once, intersects more than once, then you know the inverse of f will not be a function. Okay? So, for example, okay, is it one-to-one? Right? I have a graph of a line there. Does it pass the horizontal line test? Yes. So, will its inverse be a function? Yes. And therefore, is it one-to-one? Yes. Okay. Contrast that with, let's say, a parabola. Okay. Is a parabola a function? Yes. So it passes the vertical line test. Does the parabola pass the horizontal line test? No, it does not, right? There's any number of places you could draw that horizontal line, and it's going to intersect, you know, more than once. So will its inverse be a function? Will the inverse of this be a function? No. And so is this one-to-one? No. Okay. And you can see it, right? What's happening? 2 x values go to 1 y value here, whatever this, you know, mystery y value is, so the red intersecting the y-axis there. 2 to 1. Okay? A parabola is at best 2 to 1, but not 1 to 1. Okay? So that's the idea. Right. Now remember, we did just talk earlier, right, about there we go. We did talk earlier with square roots and squares and stuff like that, right? And we had to restrict the domain. And by restricting the domain, we created a scenario where our functions were one-to-one, right? This root 2x minus 3 is one-to-one, and then when we did its inverse, we had to restrict the domain in order to then keep that, maintain this, maintain the one-to-oneness there as well. Okay? And the inverse nature too. Questions on anything? All right, well that's it then, okay? That's all, folks. So, what I've got for you on Google Classroom, I've posted the homework. It's out of the book. Okay. I also have posted the test review as well, if you prefer to take a look at that instead. I want to briefly introduce you to the test review, so that way you can kind of be, I don't know, just so that way you don't have any questions on it and stuff like that, because it maybe is organized a little bit strangely.